Here. All right. Dividing polynomials, chapter 5, section 4. This is going to be pretty quick, so hang on. Um, do you remember long division, dividing numbers and stuff? We want to do a very similar process to that with dividing expressions, typically polynomials. And so I wanted to start with an example of dividing numbers because it may have been a while uh, since you've done this, like maybe fifth grade or something. I don't know. Um, Over here, we're taking the number 178, want to divide that by 3. Okay, and the process that we do that by on paper anyway is called long division. And if you remember, you take this number on the outside 3 and you say, will it go into 1? And of course, the answer is no. And so then you go over here to the next one and say, oh, will it go into 17? And the answer is yes, it will go into 17. And you got to know your multiplication tables here to make this work. But 3 times 5 is 15. 3 times 6 is 18. So that's 6 is too big. It goes in there 5 times. So you put the 5 up here and then you multiply it back. 5 times 3 is 15. That gets written under here and you are subtracting that and you draw a line. 17 minus 15 would be 2. And then the next step is to drop the next digit down so that you've got that. And then you start over again. You say, all right, now I want this 3. Will it go into 28? Of course it will. And you start running through your multiplication tables. 3 times 6 is 18, 7 be 21, 24, 27, 30. 30 is too big. That would be 3 times 9 would give me 27. So you put the 9 here, multiply it back. 9 times 3 is 27. You put it here, draw a line, you subtract, and 1 like that. Now you can keep going. You can add a decimal place and zeros and drop the zeros and keep going. But this 1 here was what we called a remainder. And somewhere down the line, it could work out so that you get 0 remainder, nothing left over there in this process, which means the thing terminated. You can see right here that we're taking a 1 and dividing by 3, and that's a third, which is 0.33333333 forever. This one's never going to terminate. So you had some options. You could express it as a decimal, like this, and sometimes you draw a bar to say just do that forever. You could say 59 and a third. You could also say 59 remainder 1. Does that look familiar at all? Um, so that's how you do it with numbers. And we can do exactly the same thing with algebraic expressions, and polynomials would be a big part of this. Why would we want to do this? Well, maybe there is a polynomial and we're looking for the root. So maybe f of x equals 5x squared plus 3x minus 2. And we get busy and we try to factor this thing and we go, shoot, man, that won't factor at all. And um, but maybe it's a rational expression, 5x squared plus 3x minus 2 over x plus 1. And we're going, I sure would love to cancel that x plus 1. I wonder if there's an x plus 1 in the top, and if I could factor it and get that out, and just cancel it. That would make my life a whole lot simpler. Or maybe, like I say, it's a polynomial and we're looking for the roots and we start guessing numbers and say, I think that x plus 1 might go in there. Let's try that. Okay. There is this process. We also call it long division for these expressions. But here, in the same way that we took this 3 and we tried to go into the 1, it wouldn't go. Went into the 17, though, and we put it up top and multiplied that back and subtracted. It's the same process. Take the x and say, will it go into the 5x squared? Is there something topside that I could put right there that multiplied by x would give me 5x squared? And the answer is, well, yeah. I could put 5x up here, and when I multiply it back, 5x times x would be 5x squared. I also have to multiply it by the 1, though, and that would go over here, And just like on with the numbers, we drew a line and we subtracted. So over here, I need to draw a line and I need to subtract. It's actually this whole thing that I'm subtracting. So some parentheses might be in order there, unless you can just remember to do that. But when I do that subtraction, I've got a 5x squared minus 5x squared. So that's going to be a 0. And then I come over here and I've got 3x minus the 5x would give me negative 2x, like that. Okay. Next thing we did with the numbers was take that 8 and drop it down. So over here, yikes, sorry, got to take that negative 2 and drop it down. All right. And then like we did with the numbers, we start over. We do it again. So right here, I'm going to um, clean up a little bit, and I'm going to start over again. And so here comes the second round of this thing where um, I need a number right here that multiplied by x would give me negative 2x. Okay, well, I got the x tied up. He's good, but I do need a negative 2 there. So I got to multiply it back by both of these guys and put it down there underneath. Negative 2 times x would be a negative 2x. Negative 2 times this 1 would be a negative 2. And I draw a line and I want to subtract. And here I have negative 2x minus negative 2x. That's really a plus 2x. So those cancel and I get a 0. And then I move back to the next one, negative 2 minus a negative 2. That's really plus 2. So that would be a 0. There's no remainder here. And what that means is that if, this division worked, it went in there. That's good. That's what we're trying to do. I kind of think of this as like the old nutcracker, right? We've got some kind of expression and we want to crack that nut so we can get in there and eat the meat of it, or in this case, find the roots of it. We just simplified this expression. And over here we're talking about two possibilities of why you might want to do this. Um, Dang, where'd it go? There it is. Okay. So this thing right here, the 5x squared plus 3x minus 2x is really all of this, x plus 1 times all this stuff on top, 5x minus 2. And if we had been clever enough, we could have found that by factoring. But, sometimes you need a little bit of help, and this is the help that it takes. How did we get x plus 1? In this case, we would have had to guess it. Maybe we looked at the graph and it looked like it crossed at negative 1, and we said, is that really negative 1? And so we tried it, um, and it does. Okay. So maybe we're factoring to find the roots. Down here, if it was a rational expression, I could rewrite that top as x plus 1, 5x minus 2. I've got that x plus 1 on the bottom. And that means that the one on top would cancel the one on the bottom, and we get to simplify this thing. So there's different places that you can use that. But again, it's kind of like cracking the nut open. You're trying to take that trinomial and break it down into a couple binomials and seeing what you have. Here's a couple more. Um, I've got this one on the left right here, and I'll kind of run through the steps. If you have questions about these, we can do more in class and everything. But again, you're taking this first term and you're saying, I need something up top that multiplied by the x will give me 2x cubed. So that would be a 2x squared. And I multiply it back. 2x squared times x would be 2x cubed. 2x squared times 2 would be a 4x squared. 2 times 2 would be 4, got the x squared there. That is a positive. Positive times a positive. And you do have to watch your signs like crazy in this because that'll eat you up if you mess it up. Remember how we needed to write that under there and then subtract. Draw the line and subtract. So there's those parentheses to make sure we remember to subtract 2x cubed and subtract 4x squared from these. 2x cubed minus 2x cubed would cancel. Negative 3x squared minus 4x would be a negative 7x squared. And then I drop the next one down, plus 4x right there. Okay, and now I start over again. So for round two, we'll come in here, and I need something up here on the top that will give me this negative 7x squared. So that's going to be negative 7 times x, multiply it back times x would give me negative 7x squared. Negative 7x times 2 is a negative 14x. And I draw a line and I subtract. Okay. Negative 7x minus negative 7x. These should always cancel, by the way. That first term should always cancel. If it doesn't, then something went a little bit funny and you need to go back and look at it. When I subtract a negative 14, that's really adding 14. So I would get an 18x. And then, of course, I drop the next decimal. In this case, it's not a decimal, it's the next term, but same idea. All right, round three, do it one more time. I need something on the top times x that will give me 18x, positive 18x. So that would be a positive 18. Multiply it back times x would be 18x. 18 times 2 is 36. And I draw a line and subtract. Okay, 18x minus 18x is going to cancel. And 5 minus 36 would be a negative 31. That is my remainder. This one did not go in there. Sometimes it does, sometimes it doesn't. Remainder. Um, we want the ones that do go in there. So x plus 2 wouldn't really help us crack this nut. Um, with that remainder, you want things that do go in there. So you'd go and try something else. You say, well, what about x plus 1? And you go through again. That didn't work. X plus 3, x, I usually pick things that are close to 0. Um, I like, 1, 2, and 3, positive, negative, 1, 2, and 3. And if you don't get anywhere there, then it's probably time to go look at your calculator or something, to figure out what you need. All right, here's one more of these. And then I've got one more trick for you, kind of an alternative method. But if I take 3x and multiplied it by 2x squared, then that would give me a 6x cubed, and 2x squared times the negative 2 would give me a negative 4x squared, and we are subtracting. 6x cubed minus 6x cubed would cancel those, and 11 minus a negative 4 would be 15. Minus negative is really plus right there. I drop the next term. These kind of become very mechanical once you've done a couple of them. I won't ever say that they're fun, but the more of these you can do, then the easier they get and the more comfortable you get with it. I do remember to subtract that whole deal though, and make sure you always get a 0 on that term. Negative 31 minus a negative or plus 10 would be negative 21x. Drop the next term down 15, looking for something that'll give me negative 21x, so that would be negative 7. Negative 7 times the 3x would be negative 21x. Negative 7, negative 2 would be plus 14. I am subtracting. Not going to quite work out, is it? Okay. These will cancel. The 15 minus 14 leaves me a little bitty remainder. It almost went, um, but not quite. So, those are some examples there of long division. I hope I didn't rush that too much. I hope I didn't go too slow and bore you to tears. Um, but just wanted to throw that out there. This is the last thing that I wanted to show you here. This is an alternative way to do it called synthetic division. Um, I don't really do this. Um, it seems like a trick to me, and I don't like tricks. I like to know why things work, and I like to understand the math behind it and everything. this is kind of kludgy in my mind. We've already done this problem, so let me just write what we got up here before. This was the well, I think that first one that we did, and this one had a remainder, so it's not one we want to do anyway. But just when we get done with the synthetic division, we ought to be looking at this right here. And it did have a remainder of negative 31. We did it a couple slides back. So that's what we that's what we got when we did long division with it and everything. Here is the synthetic division on this thing. I need to take out the x's and just focus on the numbers. Instead of working with the x's, we're working with the numbers. So that 2 is there, and we're going to put the 2 here and kind of draw it upside down traditionally this way. All right. And then again, I'm taking out the 2. So I'm interested, not the 2, taking out the x's. So now I'm interested in these numbers, and I'm going to put them right here beside it. So I've got a 2 and a negative 3 and a 4 and a 5. Okay. So step one, forget about all the x's. Just erase them. Okay. They're not there anymore. They are there. But we're representing it in a different fashion. In the divisor, write k minus x and write the k outside. So that constant right here is this. And there's one more thing I got to do. See how this is a plus 2? And the format says I need this to be um, x minus k. So that k right there is going to have to be a negative 2 so that when I subtract negative 2, I'm really adding 2. So that's kind of a thing you got to remember to do right there. But that should take care of that. Okay. Drop the lowest coefficient. Okay. What they mean there by that, maybe that's not the best way to do it, but it's kind of like we used to drop the next digit or the next term or something. So we're just going to drop that one straight down. And then we're going to multiply and add till we're done. We're going to take the 2 up here, I'm sorry, the negative 2, and multiply that by the 2. Negative 2 times 2 is a negative 4. So that's going to go right there. Next up, we're going to add. When we did it the other way, we subtracted, but now we're adding. So I multiplied and I add. Negative 3 plus negative 4 would be negative 7. And I do it again. Okay. Negative 2 times the negative 7 would be positive 14. Add. 4 and 14 would be 18. Take the negative 2, multiply by the 18. That's going to be a negative 36. I put it here, and I'm adding. So that would be a negative 31. Okay. We started off with x cubed here, and we kind of erased all that. It's going to knock it down. So this is really going to be 2x squared minus 7x plus 18. And this last one is our remainder. Okay. And this is the way, this is what you would get with synthetic division. And up here, you'll see with long division, is back on a slide or two ago, we got exactly the same thing with long division. So this is an alternative way to do it. Uh, I don't like it, but it's there. I can pull it off. I always just go for long division. I'm not lazy enough to leave out all those X's and things, and I just like things that I know work and why they work. So whatever, it's there. Use it if you want it, but that's the gist of synthetic division. Okay, that's all I got for today. So thanks, and let me know what I can do to help. And if questions come up, send them to me. Have a good day.